Welcome to the Foundry by Forge College. Today, we're diving straight into the actual engine of blockchain performance, the true mechanics of parallel execution. If you've ever stopped and wondered, how on earth does a network process thousands of transactions all at the exact same time without, everything crashing into a tangled mess, we are going to figure that out together. In this explainer, we'll be unpacking the elegant, kinda strict, but highly logical rules that C-Level relies on to make parallel execution a reality.
So here is our game plan for today. First, welcome to the library. 2, core concepts of parallelism. 3, the librarian mental model. 4, the C-level workflow. 5, designing for parallelism. And finally, conclusion and next steps. Let's get into it.
Welcome to the library. This is all about bridging observability and execution. Now, if you hung out with us for our previous lesson on observability, you already know how to use trace points to spot performance bottlenecks. But that brings us to a really massive question. How does C-Level actually convert those observable access patterns into actual simultaneous execution? Like, we can spot the bottlenecks all day, but how does the system look at this giant pile of incoming transactions and decisively say, okay, you, and you can all run at the exact same time?
Let's find out in Section 2, Core Concepts of Parallelism. These are the foundational architectural rules.
All right, let's peel back the curtain a bit here. The absolute foundational rule revolves around what we call a read-write set. Think of this as a highly concise map. It outlines exactly which accounts a specific instruction sequence intends to read from and which ones it intends to write to. Mechanically speaking, C-Level pulls this map directly out of the transaction message and the account metas attached to each instruction. It's essentially the runtime's way of formally declaring exactly what state a transaction is going to touch. And frankly, that is the absolute prerequisite for figuring out if a transaction is truly independent from all the others.
Next up, we have state isolation. Think of accounts as the fundamental units of mutable state on the network. State isolation is essentially this critical safety net that ensures concurrently executed sequences absolutely cannot observe each other's partial, half-finished updates. Right? Like, if one transaction is right in the middle of modifying an account, no other transaction is allowed to peek at it. This incredibly strict isolation is what preserves determinism. It keeps parallel execution from devolving into total, unpredictable chaos.
Moving right along to Section 3, the librarian mental model, rooms, badges, and very strict rules.
Okay, to really internalize how this whole lock system works, I want you to imagine C-Level as a very strict, no-nonsense librarian. In this library, every single on-chain account is a private reading room. Now, if a transaction just wants to look inside a room, say like doing a simple bank balance check, the librarian hands out a shared reader badge. And the coolest part? The librarian can hand out dozens of these reader badges for the exact same room, all at the same time. Readers can totally party together. But if a transaction wants to actually modify a room, like executing a token transfer, it needs an exclusive writer badge. The moment someone holds a writer badge, the librarian completely locks down that room. 0 other writers and absolutely 0 readers are allowed inside until that modification is completely finished.
But naturally, there's always a twist, right? You've got to beware the unpredictable assistant. In our little library analogy, cross-program invocations, or CPIs, are kind of like sending your assistant into another room to fetch something for you. The big problem is your assistant might suddenly decide they need to open 3 other rooms that you never even mentioned to the librarian. Because this dynamic behavior can bring totally unexpected accounts into scope, the librarian, or the runtime, has to be incredibly conservative. It will aggressively lock down potential conflict points just to be safe. So keeping your declarations accurate? Yeah, it's absolutely paramount.
Let's shift gears a bit. Section 4, the C-Level workflow, from pre-flight straight through to execution.
Now that we've got our strict librarian metaphor down, let's look at the literal engineering machinery that handles these badges. This happens across 6 distinct steps. When a transaction first arrives, it starts at step 1, pre-flight. This is where basic signatures and formats are validated. Step 2 is normalization, which basically sorts the account list into a standard canonical order. Step 3, read-write resolution, conservatively handles those unpredictable assistants we just talked about, the CPIs. Step 4 is really where the magic happens, constructing the dependency graph to perfectly map out all potential conflicts. Step 5 is batching all those non-conflicting groups together. And finally, Step 6, execution, where the worker threads acquire their locks and actually get to work. It's super interesting because you can clearly map each workflow stage right back to its implication for parallelism. Normalization is what makes comparing sets deterministic. Batching is what directly enables the concurrency. But really look at that dependency graph stage. It defines exactly what must be serialized. If you think back to our previous observability lesson, this is exactly where those heavy dependency graph edges come from. A really dense web of dependencies here is a huge red flag indicating intense application-level contention. As you progress through your learning journey with Forge College programs, you're going to realize that mapping your telemetry data back to these specific workflow stages is essentially an absolute superpower for optimizing your decentralized apps.
All right, let's get practical. Section 5, Designing for Parallelism, your engineering takeaways.
We've seen exactly how the engine works, so how do we actually drive it effectively? The crucial thing here is applying these 3 practical strategies to maximize your concurrency. First, isolate accounts for independent actors. Literally, do not force everyone through a single state bottleneck. Second, ruthlessly minimize shared writable accounts. Seriously, remember the librarian. Shared read-only accounts are amazing, but a single shared writable account forces absolutely everyone to wait in a single file line for that exclusive badge. And third, explicitly declare your CPI account dependencies. If you give the librarian a perfect, upfront list of every room your unpredictable assistant might visit, the runtime doesn't have to guess, and that vastly increases its ability to find independent work and run it in parallel.
Wrapping things up with Section 6, Conclusion and Next Steps, Getting Ready for the Scheduler.
So we've covered the fundamental rules today: read-write sets, state isolation, and the lock system that makes it all a reality. Now, I have a challenge for you. If you go check your execution traces right now, which library room is causing your biggest bottleneck? Is there a shared writable account that's secretly forcing all your transactions into a single file line? Finding that bottleneck is your next logical step. And honestly, this perfectly sets the stage for our upcoming lesson, which is all about scheduling and conflict detection. To continue mastering these advanced Web3 concepts, definitely head over to Forge College. Keep exploring, keep building, and I will see you in the next Explainer.